Hello everyone, welcome to the YouTube channel of TriboNet. My name is Manoj. Today, let us learn about Prandtl Tomilson Friction model. The Prandtl Tomilson model was introduced in 1928 as a conceptual framework for single atom contact friction described as a point mass dragged over a sinusoidal potential by a spring. Although it remained largely overlooked for decades, recent experimental validations have demonstrated its relevance for contacts involving tens to hundreds of atoms. Today, the Prandtl Tomilson model is widely recognized as the highly insightful mechanical analog for understanding atomic scale phenomena at the sliding interfaces. What is the historical perspective of this model? The field of nanotribology emerged in the late 1980s, which was a significant leap in the friction research by enabling the study of nanoscale contacts with the tools like atomic force microscopy. Among its notable breakthroughs was the observation of the individual atomic hopping events over a corrugated interface potential. With atomic periodicity, these events revealed a stick-slip motion that revitalized interest in Prandtl Tomilson model, an older conceptual framework. Historically, the Prandtl Tomilson model is often attributed to G.A. Tomilson in 1929 paper, which led to an alternate name, the Tomilson model. However, the theory underlying this PT model was first presented in Ludwig Prandtl's 1928 paper, which was initially inaccessible to much of the scientific community due to its publication in German. This oversight was corrected in 2012, where an English translation of Prandtl's seminar work was published, finally clarifying the fundamental or foundational role in the modern nanotribology. What does this model say? The PT model today forms a cornerstone of our understanding of the atomic scale friction. In this model, a point mass moves over a periodic potential as illustrated in the figure 1, explaining a wide range of experimental observation. Here in this figure, it shows the basics of the PT model where a point mass is connected to a supporting body M via a spring, which is effective spring constant Ce effective. The mass interacts with the periodic potential V with a periodicity A. During the sliding, the supporting body M moves with a velocity V in the x direction. If the spring is sufficiently soft, the resulting motion exhibits a characteristic stick-slip behavior. The point mass remains in a potential minimum until the spring tension reaches a critical value at which the point it jumps slips to the next minimum. The model also predicts temperature effects, which can be introduced by considering the thermal oscillations of the mass. The figure 2 here shows the zero temperature at T is equal to 0 Kelvin. The lateral force is a sawtooth-like function, with a mass jumping only when the critical force Fc for the potential and the spring constant is reached. The lateral force is measured by tracking the spring tension as function of the position of the supporting body M along the x-axis or the scan position, which differs from the tip's position xt. At the higher temperature, the thermal activation allows the mass to jump at the forces lower than Fc due to the thermal energy kBT, which is also called kBT Boltzmann constant. As a result, a maxima of the lateral force and the overall frictional force decreases and thermal noise becomes visible on the rising leg of the sawtooth pattern. Further, the schematic of the 3 here shows the macroscopic mechanical model created by Prandtl to demonstrate the stick-slip behavior same as that of the atomic scale model, illustrating the generalizability of the concept. The PT model has successfully examined or explained friction phenomena across various systems, including flat surfaces with different atom types, velocity and temperature dependence, atomic scale steps, and ions in a trap. Notably, despite its origins as a single atom model, the PT model provides an intuitive explanation for many fundamental properties of dry friction. What are the limitations of this model? Extrapolation of the macroscopic scale. While the PT model effectively explains the friction at the atomic scale, it remains challenging to extrapolate its findings to the larger or the macroscopic contacts. Scaling up from the nanometer-sized contacts to the macroscopic rough interfaces has not yet been fully resolved. This limitation stems from the difficulty in translating the atomic scale behaviors into statistical models for complex or rough contact surfaces. Similarly, complexity of the real-world surfaces. The PT model primarily addresses idealized single atomic contacts in a real-world application, surfaces are often non-ideal, featuring the defects, surface steps, impurities, and varying chemical activities. These factors influence the friction and are not adequately captured by the simple model, limiting its applicability to the more complex system. And then structural lubricity and superlubricity. Although the phenomena like structural lubricity or superlubricity have been observed at the atomic and small scale contacts, the PT model does not fully account for how the friction behaves in the presence of this phenomena when the area of contact is large. The scaling of the friction with the contact area remains at a significant challenge, and the model's predictions for a real rough contacts are still incomplete. These are the references for the information provided in this video. In this video, we understood the introduction to the Prandtl Tomilson model, what are the historical perspective of this, and the explanation of the model. Thank you for watching this video, and to get more details on the topics related to tribology, follow us on our social media pages on Instagram, Facebook, LinkedIn, and do not forget to subscribe to our YouTube channel TriboNet. Also visit our website on www.tribonet.org.